Alright, number one is just a basic equation here that we just need to solve. So when we solve a basic trig equation, we just want to get sine x by itself here. Now, so first thing, let's isolate that by adding 1 on both sides. So we'll get 2 sine x equals 1. And now we can just divide both sides by 2. Get rid of that 2. So we get sine x equals 1/2. Okay, so on my unit circle, I'm going to find where the y-coordinate is 1/2. And so sine would be 1/2 at pi over 6 and at 5 pi over 6. Okay, number 2 is another basic one here. Again, we just want to isolate sine theta. Now we need to combine our like terms here, so I'm going to subtract this 3 sine theta over. And I can subtract this and combine these. It's perfectly okay because they're both sines and the arguments there are the same. So now this will give me 5 sine theta plus 5 equals 0. Now we'll get rid of the 5 because I'm isolating sine theta there. So we get 5 sine theta equals -5, and now we'll get rid of the 5. So -5 divided by 5 is -1. Sine would be -1 here at 3 pi over 2, I believe. Okay, number 3. Now, on 3, 4, and 5, I believe here, what we get on these is we have a coefficient. We have the 2x. So what we need to do with that here is use our general forms of our answers because we have that coefficient. So let's substitute here a for 2x. So we get sine of a equals -1/2. Okay, so now if I look at my unit circle here, sine is -1/2 at 7 pi over 6 and 11 pi over 6. But there again, since I've got this coefficient up there, I'm going to have to give that general formula of the plus 2 pi n. Okay, now let's substitute our 2x back in for a. So we'll get 2x equals 7 pi over 6 plus 2 pi n. Same thing over here. So now let's divide by the 2. So we'll get 7 pi over 12 plus pi n. And on our other equation here, we'll get 11 pi over 12 plus pi n. Okay, now let's let n be different values here. So let's start with the n being 0. So if n is 0, we're just going to get 7 pi over 12 and 11 pi over 12. Okay, now let's let n equal 1. So if I let n equals 1 here, I'm just going to think of this as 12 pi over 12. So 7 pi over 12 plus 12 pi over 12 is going to give me 19 pi over 12. Okay, for my other one here again, I'm going to let, if n equals 1, then I'm going to think of that as 12 pi over 12. So 11 pi over 12 and 12 pi over 12 would be 23 pi over 12, which is almost too big, but that's just under 2 pi there. So now, if n is equal to 2, if n equals 2 here, we're going to get 2 pi, and anything positive plus 2 pi is going to be bigger than 2 pi. So any n values bigger than 1 are going to be too big. So now we just have these 4 solutions. Okay, number 4, we have yet another coefficient here of 2. So we're going to make that substitution. We're going to let a equals 2x. So we'll get cosine a equals 1/2. And so cosine is 1/2 at pi over 3. And Where else? 5 pi over 3. Okay, now there again, we've got that mean coefficient there, so we have to do this plus 2 pi n thing. Okay, now let's make our substitution back with a. A was equal to 2x, so 2x equals pi over 3 plus 2 pi n. Basically the same thing on our other equation here. Okay, now let's go through and divide everything by 2. So we'll get x to be pi over 6 plus pi n. And on this equation, x is going to be 5 pi over 6 plus pi n. Okay, now if we let n equal 0, then we'll just get pi over 6 and 5 pi over 6. And if we let n equals 1, okay, if n equal 1 here, then that would just be pi, or we could think of it as 6 pi over 6. So pi over 6 plus 6 pi over 6 is going to give me 7 pi over 6. And then, again, if n is 1, I'm going to think of that as 6 pi over 6. So 5 pi over 6 and 6 pi over 6 would be 11 pi over 6. Now notice again, it's a lot like the last one here. If n is equal to 2, then this is 2 pi. And pi over 6 plus 2 pi is going to be bigger than 2 pi. So we only want, again, the solutions that go from 0 to 2 pi, and that's all. So we just have these 4 solutions here. Okay, number 5, we have yet another coefficient, okay, x over 2. So I'm going to let a equal x over 2. So we'll get tangent of a equals negative square root of 3 over 3. Now, where is my tangent here? Negative square root of 3 over 3. So tangent is negative in the second and the fourth quadrant. So that's going to be at 5 pi over 6. And let's see where else. At negative 11, or I'm sorry, 11 pi over 6. Now, we got the coefficient here, so we have to do this unfortunate stuff. We got to add the 2 pi n. Now, a, recall here, was x over 2. So we get x over 2 equals 5 pi over 6 plus 2 pi n. And I made a mistake here. This was tangent. So, yeah, it just should be pi n. Did y'all catch that? I caught it too. Okay, so there we go. All right, so plus pi n. Okay, same thing over here. All right, now let's get rid of the 2 here. So we don't divide by 2 here. Instead, we do the opposite. We're going to multiply by 2. Okay, so they'll cancel out real well there for me right there. And say 2 goes into 6 3 times. So I'll get 5 pi over 3. And then 2 times pi n is 2 pi n. Okay, basically the same thing over here. Those go away. So 2 goes into 6 3 times. So that'll be 11 pi over 3 plus 2 pi n. Okay, now let's let n equal 0. So if n is 0, then x is going to be 5 pi over 3. And notice here, 11 pi over 3, think about it, 6 pi over 3 would be 2 pi. So that is too big. Okay, so really, this is all I'm going to have. All the other solutions end up here just being too big, because 11 pi over 3, okay, would be bigger than 2 pi. So it's only one solution there. I believe that's all the ones with the coefficients. Now we're moving on to the quadratic ones here. So this quadratic doesn't have a linear term, so we can solve it by the square root method. So sine squared x, and we'll just add the 3/4 over here and be positive 3/4. Now we're going to take the square root of both sides. So numerator and denominator, my fraction. So we get sine x. And recall, since we take the square root of both sides, we need to say plus or minus here, square root of 3 over 2. So we're going to find on our unit circle, where is the sine square root of 3 over 2, or negative square root of 3 over 2. So that would be at pi over 3 and 2 pi over 3, 4 pi over 3, and 5 pi over 3. Right, number 7. It's a quadratic form, and this one we can't do by the square root method because we have a linear term. So we're going to use our substitution and factor method. So I'm going to let a be sine x. So this will give me 2a squared minus 3a plus 1 equals 0. So now we're going to look for factors of 2 that add to give me 3. So that would be 2 and 1. And notice I'm splitting because I had a leading coefficient. Sine's positive, so both are going to be the same and be negative. Okay, now let's group it. So the first group will get 2a. That'll leave me with a minus 1. I can get out a negative 1. That'll leave me with another a minus 1 like I need there. So we'll get a minus 1 times 2a minus 1. So a is going to be 1, and then a is going to be a half. Okay, now recall that a was just sine x. So we're looking for where is sine x equal to 1, and where is sine x equal to a half. So sine would be 1 at pi over 2, and sine is equal to a half at pi over 6 and 5 pi over 6. Okay, on number 8.
Please point this interruption.
Now, our equations here starting with number 8, the directions say to try to use an identity. So notice I can't really factor it like I did the last one because they're different. I have a sine squared and a cosine. So what I'm going to use there is a Pythagorean identity. Sine squared could be written as cosine squared minus 1. So I'm making a substitution there for sine squared with that. Now continue the rest of it, and notice that's going to go with my cosine much better. Now let's put together our like terms. Negative 1 and 5 there will give me 4. So I get cosine squared x minus 5 cosine x plus 4. Okay. Now factors of 4 that add to give me 5 would be 4 and 1. Oh, I probably wouldn't do with my substitution here. A squared minus 5a plus 4 equals 0. Factors of 4 that add to be 5 would be 4 and 1. Now, I'll get a is 4 and a is 1. Now, since this value doesn't fall in between 0 and 1, and a is cosine x, well, it has fallen between 0 and 1. Well, it's not going to give me any solutions. So I'm not worried about that one. Now, this one does fall in between 0 and 1. So a is cosine x. So where is cosine 1? So cosine would be 1 at 0. Okay, number 9. And here again we have a cosine squared and a sine. So again, what would work better right there would be a sine squared. So I'm going to substitute for cosine squared here, 1 minus sine squared. So now I'll have to bring down the 2 and distribute it. And let's bring down the rest of the equation here. Okay, so now that's going to go with that sine x a lot better there than that cosine squared one. Now let's distribute the 2, so we'll get 2 minus 2 sine squared x. Now I'm going to group everything over on the right side so I can make this positive. And again, because it's a quadratic form, I want it set equal to 0 here. So I'm going to add that over, and it's going to be a nice positive 2 sine squared x. We'll bring down 3 sine x, and then we'll take the 2 over and subtract it from there, and that'll just be a positive 1. Okay, now we can use our substitution and factor now. So factors of 2 that add to be 3 would be 2 and 1. It's kind of too late now. I'm sorry, I forgot about it. All right, now I'll group them here. So we'll get 2a times a plus 1 plus 1 times a plus 1. And now we can bring out that a plus 1. So we'll get a here to be negative 1 and negative 1/2. Now recall a was sine x. So we get sine x is 1 and sine x is negative 1/2. Now let's find out here, where is sine 1? And that would be at pi over 2. And then where is sine negative 1/2? Right, that's going to be at 7 pi over 6. And 11 pi over 6. Okay, number 10. Again, we're going to make a similar substitution here. We have sine squared and cosine. Now, what's going to go a lot better there is cosine squared. So now what we can do here is just substitute for sine squared 1 minus cosine squared. Now I'm going to continue with the rest of it here. Okay, now let's put together our like terms here. We can put the 1 and the 6 there together, and that's going to give me 7. So I'll be left with negative cosine squared x minus 6 cosine x, and then plus 7. Okay, now let's get rid of the negative, so let's just distribute a negative through. So it can be nice and positive when we factor it. Now let's use our substitution. So now we've got here a nice quadratic form here. So we do a squared plus 6a minus 7 equals 0. Factors of 7 that subtract to give me 6 would be 7 and 1. Notice we didn't have a leading coefficient right here, so I didn't have to split it. So now this is going to be plus 7 and minus 1. So we're going to get a is equal to negative 7 and a equals 1. Now, a problem we have here, negative 7 doesn't fall in between negative 1 and 1, so it's not going to lead me to any solutions. So 1 is the only one that I'm really going to get. Now, a, recall, was cosine x. So I have cosine x equals 1, and cosine here would be 1 at 0. Okay, on 17, again, we're going to use the same similar strategy here by using a Pythagorean identity to make a substitution right there. So for sine squared x, we can write that as 1 minus cosine squared x. And I'll just take the 2 in front there and just distribute it through. So now if I multiply by 2 there, we're going to get 2 minus 2 cosine squared x. And bring down the rest. Okay, we'll put together my like terms here. 2 minus 1 is just going to give me 1. Okay, now let's, again, we'll get rid of the negative. Now let's make our substitution and use our nice quadratic form here. So 2a squared plus a minus 1 equals 0. Now we'll have to split this one. We got the leading coefficient. Factors of 2 that subtract to be 1 would be 2 and 1. So there'll be different signs here. It'll be plus 2 and minus 1. So my first group there, we could factor out a 2a. And then the second group, a negative 1. So we'll get a plus 1 times 2a minus 1. So a is equal to negative 1 and then a positive half. Okay, now recall the a was just cosine x. So we have cosine x equals negative 1 and cosine x equals a half. So cosine is negative 1 at pi, and cosine is a half at pi over 3 and 5 pi over 3. Let me check that 5 pi over 3. Yeah, that's right. Okay, now we're getting away from the squares in the Pythagorean identities here, and notice what's popping up here is the 2x. So what I'm going to be using here is a double angle for cosine. So recall our double angles for cosine here. We got cosine 2a is equal to 2 cosine squared a minus 1. Okay, or we could use the other formula here, 1 minus 2 sine squared a. So we have to decide here which one's sort of better. Now, since the rest of the equation here has a cosine in it, the one that I want to use would be this one with the cosine squared. So I can have a nice quadratic form there. So I'm going to substitute there for cosine 2x, 2 cosine squared x minus 1. Now let's just bring down the rest of it there. So minus 9 cosine x plus 5 equals 0. Now I'll combine some of my like terms here. I have a negative 1 and a 5. So negative 1 and 5 would be 4. Okay, now I've got my nice quadratic form here with my cosine squared and my cosine. So now let's make our substitution. We get 2a squared minus 9a plus 4 equals 0. Now, let's split the middle term here and factor it. 2 times 4 is 8. Factors of 8 that add to give me 9 would be 8 and 1. Both of them will be negative. Now to my first group here, I can factor out a 2a, so that'll leave me with a minus 4. Factor out a negative 1 here, so that'll also leave me with a minus 4. So we'll have a minus 4 times 2a minus 1. So a is 4, and then a would be a half. Now, since 4 doesn't fall in between negative 1 and 1 here, it's not going to lead me to any solutions. Now, a half does, though. So recall cosine is equivalent to a. Cosine x is the same thing as a. Cosine is a half, and cosine would be a half at pi over 3 and 5 pi over 3. All right, on 13, now there again we got cosine 2x. I'm going to copy these formulas over here. So in this case, again, it's just a double angle for cosine, but this time we're going to use this one. If I've got over here a sine x, then what's going to go better with it would be a sine squared as opposed to a cosine squared. So for cosine of 2x right there, I'm going to substitute there 1 minus 2 sine a, or 1 minus 2 sine x. Now, let's write the rest of it here. And notice here I've got a nice quadratic form here. Now, it's not set equal to 0, so we can do something about that. So I'm going to pull everything over to the left side. I'm going to subtract 1 from both sides here. Now, that's just going to make that go away. And we'll add the negative 2 sine squared to the other side, so I'll make it positive. So this one's a little different. It's got a linear term, but it doesn't have a constant term. So what we're going to do here is we're just going to factor out a sine x. So we get sine x times 2 sine x plus 1. Now we'll just set both of them there, both factors equal to 0. So we'll get sine x equals 0, and then 2 sine x plus 1 equals 0. So sine is 0 at 0 and pi. Now let's solve this one. I'm going to subtract the 1, and then I'm going to divide by the 2. And so let's see, sine is negative 1/2 at 11 pi over 6 and 7 pi over 6. Okay, so notice we haven't really seen one like this. It was a different quadratic form here. It didn't have the constant term. So when it doesn't have a constant term like that, you can just factor out a sine x or sometimes like a cosine x there. And so we might want to look at like that and just think, well, what makes both of those factors equal to 0, and solve both of those. Okay, on number 14, another 2x right here. So again, what we're going to use is a double angle. Now, I have to figure out which double angle here to use. So I want something here that's going to go with that cosine x. So I'm going to use this double angle since it has a cosine squared. So for cosine 2x, we'll substitute 2 cosine squared x minus 1. Okay. Now this is real similar to the last one that we just did. That's why I kind of looked back here. So now I've got my nice quadratic form. Let's just set everything equal to 0 here. So I'm going to add the 1 over. So those are just going to go away. And we'll take the cosine over and subtract this. We'll get 2 cosine squared x minus cosine x equals 1. So it's another one here that's a quadratic form, but it's missing the linear term. Or this, I guess, should be 0. I'm sorry. So we can still, though, factor out a cosine x. So we'll get cosine x times 2 cosine x minus 1. And now let's think about it this way. Either of those factors could be 0. So cosine x could be equal 0, or 2 cosine x minus 1 could be 0. Now, let's see, cosine is 0 at pi over 2 and 3 pi over 2. And let's solve this one. We're going to add the 1 over, and then divide by 2. So we'll get cosine x is 1/2. Now let's think here. Cosine is 1/2 at pi over 3 and 5 pi over 3, I think. Okay, now another double angle, because I got my 2x right here. Now this one's the double angle for sine. So my double angle for sine here, sine 2a is equal to 2 sine A cosine A. So now I'm going to substitute here for sine 2x, 2 sine x cosine x. Now, so notice these two are alike here, but the terms are not like terms. So what I'm going to do is try to put them together on the same side and use factoring here. So I'm going to bring the sine x over so I can try to do something with these two things. So since I have two of them there, what I can do is just factor one out. So we'll get sine x times 2 cosine x minus 1 when I factor that out. Now, either of those things could be 0. So we get sine x equals 0 and 2 cosine x minus 1 equals 0. So let's see, sine is 0 at 0 and pi. Let's solve this one. We'll add the 1. So we'll get 2 cosine x equals 1. So we get cosine x is a half. So cosine would be a half at pi over 3 and 5 pi over 3. Okay, on number 16, this is sort of a part of the double angle formula here for sine. So the double angle for sine, it's like we just wrote there a minute ago, the sine of 2a is equal to 2 sine A cosine A. So all that's missing on this here is the 2. So to get the 2 that we need here, we'll just take both sides and multiply by 2. Okay, so now I get what I need here. I get 2 sine x cosine x equals, the 2's would just cancel over here and just leave me with 1. Okay, now we can use our double angle. So for 2 sine x cosine x, so I have a 2 sine A cosine A, we can substitute sine 2x here. So we get sine 2x equals 1. Okay, now it does give me a coefficient to deal with, which I'm not really too fond of here, but now I can at least solve it. So we'll let a equal 2x. So we get sine A equals 1. So let's see, sine is 1 at pi over 2. Now, again, because of the coefficient, we're going to have to do the general form here of plus 2 pi n. And now a is equivalent to 2x, so we'll put the 2x back in. Now we're just going to divide by 2. So we'll get x to be pi over 2 would be pi over 4. And those 2's will go away, so that'll just be pi n. Now, let's just go through our values of n here that will work. So we'll start with n to be 0. So n equals 0. X would be pi over 4. Right, let's let n be 1. So n is 1 here. This, I would just think of pi as just being 4 pi over 4. And so pi over 4 plus 4 pi over 4 would be 5 pi over 4. Now when n is 2, this is going to go to 2 pi, and that's going to be too large. Anything, of course, if you add 2 pi that's positive is going to be bigger than 2 pi. Right, now in 17, now we're just switching over to just evaluating and not solving equations here. So simple strategies, like in this case, changing everything to sine and cosine usually works here. So let's write cotangent as cosine over sine, and then we can write tangent as sine over cosine. Okay, now we've got some complicated division there, so let's do this. Let's change this, instead of dividing or a complex fraction, into multiplying here by the reciprocal. So we'll take the numerator here, which is cosine b over sine b, and multiply it by the reciprocal. So that reciprocal would be cosine B over sine B. Okay, so that's did the reciprocal there. Now, when we multiply this out, we're going to get cosine squared B over sine squared B. So recall, cosine over sine is cotangent, so this would just be cotangent squared B. Okay, number 18, here we'll just use a similar strategy. We'll change everything to sine and cosine since we're multiplying. So I can change cosecant here to 1 over sine. No, nothing cancels here. Let's just multiply it out. So we get cosine x over sine x, which is just going to give me cotangent x. Okay, number 19, let's change tangent to sine over cosine. And we'll change cotangent to cosine over sine. And so let's notice here we get a lot of stuff canceling out, so that's just equal to 1. Okay, on 22, now we're moving over to where we're seeing some squares. So what we're really going to use here are our Pythagorean identities. Let's look at the Pythagorean identities real quick. Sine squared x plus cosine squared x equals 1. Now if we divide through by sine squared, we get 1 plus cotangent squared x equals cosecant squared x. Okay, and if we divide by cosine squared, we'll get tangent squared plus 1 equals secant squared. Okay, so now let's notice 1 minus sine squared. Let's see how we can take this identity and manipulate that to see what that would be. So to get 1 minus sine squared, I would just simply subtract this over. And so 1 minus sine squared is cosine squared. Cosine squared theta there. Now for cotangent squared plus 1, well, that's just cosecant squared. And now I'm just changing to multiplying, so now I'm going to change everything to sine and cosine. So we can change cosecant squared to 1 over sine squared. So that'll give me cosine squared over sine squared. And cosine squared over sine squared would be cotangent squared. All right, on 23, let me copy my identities over here. Probably a good idea, like on our test here, to write those Pythagorean identities at the top of our paper or somewhere like that. Okay, so let's see if we can find some Pythagorean identities in this somewhere. So notice cosecant and cotangent can kind of go together right there. So to get cosecant squared minus cotangent squared, we can just simply subtract cotangent squared over. And so cosecant minus cotangent squared there is just 1. So that leaves me with 1 minus cosine squared x. Now 1 minus cosine squared x would just be sine squared x. So I could just simply here just take that cosine over. See, that would give me 1 minus cosine squared, which would be equal to sine squared. Okay, on 24, now we're kind of missing the squares on this one. So there's no Pythagorean identity here yet, so let's just change everything to sine and cosine first. So for cotangent here, we can write that as cosine x over sine x. And I think that was supposed to be, let me think about this just a minute. what happens from here now is 24 requires that you find a least common denominator. And we didn't talk about those yet. We'll actually talk about those Tuesday or Wednesday or next week here. So for right now, we'll just omit 24 here.